Porting a module is the way to gain access to the code inside it. Module is just some code in a single file. In this example, we have a print statement, a variable x, and a function named sayHi as code. Code is in a file named module1.py. Within the same directory as module1.py, we have another file main.py. In main.py, we have one line of code to import module1. Note that the file name without the .py extension is the module name. Now, let's execute the main.py file using the Python interpreter. You're seeing the output of the print statement. So, simply importing the module executes the code in the module line by line. Another thing to understand is that, just like everything else, a module is also an object in Python. Importing the module does two things mainly. First, it creates a module object somewhere in the memory. Then the module name is saved as a key in the current module's global namespace dictionary. Value corresponding to this module name will be the address of the new module object. This is the same as if we declare any other variable within the file using the assignment operator. If you check the type of module1 variable, it shows as module type. Module objects are instances of the module type class defined in the types module. Like with any other variables in Python, we can get the memory address of the module object using the id function. We can even create a new module object ourselves by passing the module name and a docstring to module type. Like other variables, you can also create an alias to the module object. Both my_mod and module1 will be references to the same object in memory. The import statement itself supports creating custom names for the module. In the next example, we are declaring a global variable x, and a function my_func. Within the function, we are printing the variable dunder file, which we didn't declare. After importing this module in another file, we can see our global variable x and function my_func among the attributes of this module object. All the variables and functions that we declare at the global scope within module1 are available as module object attributes after the import. Python also creates a few other variables like dunder file, dunder name, etc. Within module1, we can use them directly since they are available as global variables. All such symbols are stored in a dictionary of the module1 object. You can access those values by directly using this dunder dict attribute. Python also provides an easier way to access these attributes using the module name.attribute name syntax. Dunder name attribute will have the module name as its value. Module name is the same as the file name without the .py extension. Dunder file attribute will have the absolute path of the module file. You can call the function declared in module1 using the syntax. If you look at the module name in the attributes dictionary, you will get the function object. Using parentheses, you can execute the function object. Note that all the Python modules are not necessarily written in Python. Some are written in compiled languages like C or C++ for better performance. Here, the socket module is a regular Python file, but math is not. Python exposes its import system through the meta_path attribute of the sys module. Meta_path is a list of objects. To understand what these objects are, we need to know about finders and loaders. Python's import system has two conceptual objects called finder and loader. The finder's job is to locate a module, and a loader's job is to load that module. In practice, a finder is a class that has an instance method findSpec, and a loader is a class that has a load module instance method. What meta_path shows is a list of finders. So, all of those objects implement the findSpec method. Some objects implement both finder and loader. Such an object is called an importer. Based on the name of the objects themselves, you will be able to tell that the first two are importers and the third one is just finder. Next, let's try using these methods ourselves. Here, I'm saving the built-in importer object in the variable importer. Built-in importer is an importer for built-in modules. Built-in modules are different from the ones in the standard library. Built-in modules are modules that are compiled into the Python interpreter. Built-in module names attribute of the sys module returns a tuple of all such built-in module names. Since an importer is a finder, we can call the findSpec method on it and pass the string itertools to it. FindSpec method returns a module spec object. This object has information on which loader to use. Since built-in importer is also a loader, we get the same object itself. Then, you can call the load module method on the loader. This returns the actual module object. In the case of importers, both finder and loader are the same object. Next, let's see what happens if we use built-in importer to load a non-built-in module. It simply returns none. Next, let's use the Pathfinder. Pathfinder is the one that looks for Python modules under different file system paths. The list of paths it will look for Python modules is stored in sys.path. This list is initialized on program startup, and the first item in this list will be your current directory from which you run the file using the Python interpreter. Next, let's call findSpec on this Pathfinder object. It returns a module spec with information on which loader to use to load the socket module. Here, the name of the loader that we should use is sourceFileLoader. It also has the path to the socket module file. Note that here the loader is not the same Pathfinder object. We can get the module object by calling load module on this sourceFileLoader. Python also sets this module spec object as the value of the dunderspec attribute of the module. Next, let's see the whole process of importing a module in action. When Python executes the import statement, it first checks in a global cache of already loaded modules. This cache is just a dictionary with the module name as keys and module object as values. If the module is present in this cache, it's returned immediately. If not, Python's import protocol is invoked involving the previously mentioned finders and loaders. Loader creates the module object in memory. Then, an entry is added to the global cache. Sys.modules is the dictionary that maps the module names to modules that have already been loaded. Then, in our current module's namespace, we get the name module1 as a reference to the module object. What happens when you delete module1? It simply removes the reference in our global namespace. It doesn't delete the module object. This behavior is the same for any variable in Python. So, if you import the module again, the module code is not compiled and executed again. You get a reference to the existing module object. Another interesting thing is that, if there is an entry in sys.modules, no further checks are performed. Here, I'm adding an entry for my underscore test. Its value is not a module object, it's a function. Then, if I do try to import it, it completes successfully. Checking with the type function also shows that it's a function. Suppose we wanted to reload a module. We just saw when the module is imported for the first time, Python compiles and executes the module code and creates a module object. Mapping of already loaded modules are stored in sys.modules. If we delete the module name, it only deletes the reference in our current module's global namespace. The module object and its entry in sys.modules persist. This is not what we wanted. Another option is to delete the mapping stored in sys.modules. Remember, this also only deletes the reference to module object stored in the sys.modules dictionary, not the actual object. Now, if you import the module again, Python will first look in sys.modules. Since it's not there, it will compile and execute the module code to create a new module object. So, we were able to achieve what we wanted. But there is one problem with this approach. If some other module in our project had imported the module, it will still have reference to the old module object. That's why for such use cases, you should use the reload function provided by the import lib module. Instead of creating a new module object, reload will mutate the existing object in place. So all other modules that have reference to this module object will be able to see the changes. Import lib also provides many other useful functions. Import module function can be used to manually import a module without using the import statement. Find spec will return the module spec for the specified module. Next, we will see how to import a module without using the import statement. We will compile and execute the source code ourselves. Here, we have a file with one function definition. This will be the module that we will import. Within our main file, we store a name and path to the module file in two variables. I'm just setting a random value as module name. Usually, it will be the file name of the module without .py. Next, we create a module object using the module type class. Then we set the dunder file attribute of this module object to our module's absolute file system path, just like how Python does it. Then, we add the entry within the sys.modules cache. The key is the module name and the value is the module object. Next, we open the module file and read its entire content. Then, we compile this source code using the built-in compile function. Compile function returns a code object that can be executed using the exec function. Built-in exec function supports the dynamic execution of Python code. Separate compile step is not necessary because the exec function can do that internally. We also pass the module object's dunder_dict to the exec function to use as the namespace for executing the code object. Now, we can call the sayHello function defined in module 1 using the module object we created, just like if we had imported it using the import statement. Python supports a few different syntaxes for importing code. We have already seen what the basic import statement does. It checks in the sys.modules to see if the module was already loaded. If it's present there, reference to the module object is returned. If not, the module is compiled and executed to create a new module object, entry is added in sys.modules, and a new symbol or variable is created in our current module's global namespace. Note that when the module is compiled, it's not just one object that is created. Objects corresponding to all globally defined variables, functions, classes, etc., are also created. For example, the socket module defines the gethosName function. So a function object will be created in memory. The socket module's dictionary will have reference to this function object. If you do import socket as my_socket, the symbol name in the current namespace will be my_socket instead of socket. If you do from socket import gethosName, then the current namespace will only have the gethosName symbol, which will be a reference to the function object. Note that even in this case, the whole module is loaded. There is no partial loading. It's just that the current module only has access to that specific function. You can also import specific attributes with a different name. From socket import star will create symbols in the current namespace for all the symbols provided by socket. This is generally not recommended. If you look into the math and cmath modules, there are many functions with the same name. Using import this way will mask the function name from one of them. Some people use the from module import symbol syntax hoping that it only imports the module partially, and thus gets some benefit on performance or memory saving. We have already seen that's not true. In either case, Python will compile and execute the entire module. The only performance benefit of using the second style import is that socket.gethosName requires one additional lookup in the dictionary of socket module to get to the gethosName function object. Dictionary lookups in Python are super fast, and you might only see any noticeable performance benefits if you calling the function a million times or so. We already saw that a few variables like dunder file, dunder name are made available by Python in each module's global namespace. Let's focus on the dunder name attribute. Here, my code is in a file named mymodule.py. Within the sayHello function, I'm using the dunder name variable. In the end, I'm calling that function. If you execute the file directly using the Python interpreter, you will see that the value of dunder name is dunder main. Suppose I have another file within the same directory. I'm importing the first my_module in it. Since importing the module executes the code inside it, the say_hello function is executed just by importing it. But we will see that the value of dunder name is my_module, which is the module's name. If you check the value of dunder name within the current file, it will be dunder main. You can also access the dunder name attribute of the my_module from the current module. This is because, within each module, Python initializes the dunder name variable to that module's name. For the file or module which is the execution entry point, or simply put, the file which we execute using Python interpreter will have the value of dunder name initialized to dunder main. Let's see the most common use case of this behavior. Assume that we wanted our module to be capable of executing directly, and also should allow it to be imported by other modules. For that, we can add an if statement to check if the value of dunder name is dunder main. If yes, this file was executed directly. If some other module was importing this module, the value of dunder name will not be dunder main and thus functions won't be executed. Packages are a way of structuring Python's module namespaces. Just like modules can be thought of as code in a single file, packages are modules in a directory. As an example, let's look at collections and socket in the standard library. Collections is a package and socket is a module. Once you import a package or module, we get a module object just like what we saw till now. The only difference is that, for a package, this module object will have the dunder path attribute set to its directory in which the package code resides. Here, this is a directory. For modules, the dunder path attribute is not set. Python has two types of packages, regular packages and namespaces packages. We'll first look into regular packages. Consider this directory structure. Here, we have a dunder init file within the package1 directory. This is called a regular package in Python, a directory with one dunder init file inside it. Directory name becomes the package name. Within this dunder init file, we have a print statement and a function definition. In our main file, we import this package. Python will use its finders to locate the package. Here, it will use the path finder to locate package1 by looking through all the paths in sys.path. Remember that the first entry in sys.path will be our current directory. That's why Python will be able to locate package1. Notice what's happening here. You import a package by the directory name. When you import a package, the code inside the dunder init file is executed automatically. This is what becomes the compiled code object of the module object that will be created when you import a package. Now we can access the function defined inside the package, just like how we did after importing a module. We already discussed that only packages will have the dunder path attribute set on the module object. Dunder file attribute of a package will be the dunder init file. Dunder package and dunder name attributes will have the package name. Just like modules, the packages will also have the dunder spec initialize the module spec object showing which loader was used to load the module. In the next example, we have the same directory structure as before, but there is a mod1 module inside package1. Dunder init file only has a print statement. Mod1.py file has a print statement and a function definition. We would like to import this module and access the function inside it. Let's try by importing package1. Importing package1 creates a reference to the module object in the current module's global namespace. Also, like normal modules, an entry is added in the sys.modules cache. Now, if we try to access the mod1 module like an attribute of package1, we get the attribute error. So, simply importing a package doesn't import the modules inside it. The way you import the mod1 module inside package1 is using the name package1.mod1. Notice that this import executed the code inside dunder init also, which means it first imported package1, then mod1. Now we can access the function defined inside mod1. You can verify this by checking in the sys.modules cache. We'll see an entry for package1 and package1.mod1. Another thing to note here is that, in our current namespace, we will only have the package1 symbol. We can only access the submodule as an attribute of package1 using the dotted syntax. In summary, importing a module within a package will first import the package itself, thereby executing the code in dunder init, and then executes the module code. This creates one entry for the package, and another entry for the module in the sys.modules cache. Module where we used the import statement will only have reference to the package. In the next example, we have another package2 defined inside package1. If we import the module mod2 here, Python first imports package1, then package2 and finally mod2. Note that mod1 of package1 doesn't get automatically imported here. Just like before, the current namespace only has reference to package1, and you need to access the rest of them as its attributes using dotted syntax. Sys.modules will have entries for package1, package1.package2 and package1.package2.mod2. If you don't want to write the full path every time to call the code inside mod2, you can use the import statement this way. Now instead of package1, our namespace will have a reference directly to the mod1 object. Note that except for what name will be available in the current namespace, there is no difference by using this import statement. Python will still execute all modules in its path to mod2. Didn't see the print statement here, since the module was already imported and is present in the sys.modules cache. For the next example, we will reuse the directory structure we saw in the previous example. Within the dunder init file of package1, we import the innermost module mod2. Note that we are using the absolute import here. This means we start from the outermost package, that is package1. The execution entry point of our project is the main.py file. To run our project, we will be executing the main.py file using the Python interpreter. Package1 is at the same level as main.py. That's why absolute imports in any of its sub-packages start from here. In our main module, we are importing package1. But notice that we can now access mod2 through package1. In the previous examples, we saw if wanted a nested module, we had to explicitly import it using the full path. Here, we only had to import package1. How is this happening? Let's see a simpler example. Here, our module is importing the socket module from the standard library. It also defines a global variable and a function. Next, we import this module. Obviously, we are able to access all of the attributes defined in that module's global namespace. If you think about what an import statement does, it's equivalent to defining a global variable socket with value as the module object. So, just as we access global variables that we defined in the module we imported, we can also access the modules it imports. Basically, our current module's namespace has a reference to the my_module object. My_modules dictionary has symbols that point to objects that it defined, including the modules it imports. If we look back at our previous example, importing package1 executes its dunder init file. Dunder init file imports mod2, and thus we are able to access through package1 as its attribute. Till now, we were using absolute imports where we specify the full path to the package or module from the outermost one. Python also supports relative imports. So, if you want to import mod2 in the dunder init file of package2, we can either use the absolute import starting from package1 or use relative import. Relative import is where we start from the current directory. Since mod2 is in the same directory, using a relative path makes more sense. You can only use from .import module syntax for relative imports. Single dot means the current directory, two dots means its parent directory, and so on. Another important thing is that relative imports can only be used inside packages. For example, package1 and main.py are in the same directory, but we cannot import package1 and main.py using relative import. This will result in an import error. We know that Python doesn't have the concept of private attributes. However, there are some mechanisms to control what symbols are exported from a module or package. Note these mechanisms only apply when the user imports a module using from module import star syntax. First way is that any symbol that is prefixed with an underscore won't be exported. So, in this example, the first func and variable x won't be imported. Second method is defining a dunder_all variable. This can contain a list of strings, and Python will only import these symbols in the user's module. Let me show you how this is usually used in packages. Here, we have a mod1 module inside package1. Within mod1, we specify we only want to export the symbols y and second func. We also don't want the user to be aware of all the internal code organization of our package. We want them to be able to use the symbols directly on the package, like package1.y or package1.secondfunc. So, we will import all the symbols from mod1 in dunder_init file of the package. Then we specify the dunder_all of package1 to be the same as that of mod1. What you are seeing currently on the screen is the async IO package in the standard library. If you have multiple modules within your package like this, you can add all of their dunder_all attributes to construct the final dunder_all of your package. Now, let's see the second type of package in Python, the namespace package. Regular package needed a directory and one dunder_init file in it. What if we import a directory that doesn't have any files in it? Here, package1 is an empty directory. If we import it, we will see it is a namespace package. This package has all the attributes that of a regular package. Just like the regular package, its dunder_path attribute will be the absolute path to the directory. Dunder name will be the directory name. Dunder file attribute of the namespace package will be empty. For regular packages, its value will be the path to the dunder_init file. The dunder spec attribute shows it uses a special loader called namespace loader. All other behaviors remain the same as that of a regular package. You can have modules or even regular packages inside it. Here, package1 is a namespace package, since it doesn't have a dunder_init file, and package1.package2 is a regular package. Python even supports loading packages and modules from zip files. Let's compress all the contents of the package1 directory into a zip file and remove the directory. Now, we only have a zip file and our main file in the current directory. To import a package inside a zip file, the absolute file system path of the zip file must be present inside the sys.path list. Here, we are adding it manually. Now we can use a normal import statement, and Python will import the package from the zip file. You can also use the Python path environment variable. If you run the Python interpreter after setting this environment variable, those entries will be added to the sys.path. We usually run Python files by specifying python space filename.py. Python interpreter also takes a -m option to specify a module name that we want to run. Then, Python will search for that module's py file in sys.path and execute it. So here, if we want to run app.py, we can run it by specifying server.app. You can make a package executable by specifying a dunder main.py file under its directory. If you specify the package name as value to the -m option, Python will execute the dunder main.py inside it. You can have both dunder_init and dunder main files inside the same package. This setup will allow you to import it as a regular package, and also make it essentially a CLI application. Some examples from the standard Python installation are the http.server, which starts an HTTP server application, the zip file module, which supports operations with zip files, and the pip itself, which we use to install third-party packages.